So just to recall that we have discussed quadratic forms in the last lecture, and there we have seen positive definite, negative definite, positive semi-definite, negative semi-definite, and indefinite. Also, we have seen that for complex matrices, what we do, we have seen the conjugate of a matrix, A conjugate, where the elements are given A complex matrix, we take the A conjugate matrix A. Uh, any problem regarding visualizing this screen? In fact, let me join. Okay, I think it is visible to you now. Okay, right. Thank you. So, for complex matrices, what we have seen, if we have Aij, then the elements of this complex conjugate matrix is Aij conjugate. Let us take the conjugate. For z equals to x plus ij, iy, z conjugate will be x minus iy. Simply. Now, parallel concept of symmetric matrix, here it is Hermitian matrix. So for Hermitian matrix, we have seen that it is said to be Hermitian if Aij equals to the Aji conjugate. Now, if we I equals to j, for I equals to j, what we see, Aii equals to Aii bar. Okay. That means the main diagonal elements are actually real numbers, because only for real numbers we have A and A conjugate are equal. So here it is one example. of Hermitian matrix. And for Hermitian matrix, we have a property. A matrix is said to be Hermitian if and only A equals to A theta. What is A theta? A theta is take the complex conjugate, and after that you take the transpose. So then we call it a complex conjugate. Transpose of complex conjugate. So there are some properties that very simple properties that we can see. This is just an easy verification that any square matrix can be written as a sum of a Hermitian and a skew Hermitian matrix. Now, but we have not defined the skew Hermitian matrix, so we'll discuss this sometime later. Okay. But yeah, this is also later. Let us discuss this thing. Eigenvalues of Hermitian matrix are real. Okay, and then the eigenvalues of a skew Hermitian matrix are purely imaginary or zero. So these concepts are actually whatever for real matrices.
Sir, can you please show the previous slide?
Yes.
Thank you, sir.
Okay. For real matrices, what we have symmetric. And we have skew symmetric. Then we have orthogonal. So the semi-parallel concepts will be for complex matrices. And the properties that we have discussed for real matrices, that means only the characteristic and characteristic vectors, the eigenvalues and eigenvectors. So we want to study them. So this will be Hermitian matrix, parallel concept. This is Q Hermitian. So the third thing is a unitary matrix. Okay. These are parallel concepts that we are going to discuss today. So if you try to, this is just nothing much to prove, but simple proof is there. The eigenvalue of a Hermitian matrix are all real numbers. For Hermitian matrix, what we know, that means A theta equals to A. That means what is A theta? A theta is A transpose, A conjugate transpose, A theta. Now, this operations will hold for this. If you multiply with lambda and take the whole theta, then it will give you this relation. Similarly, for AB theta, it will give you this theta. Same concept as if you take AB theta, A transpose. Okay, then what we see, B transpose, A transpose, same concepts are applied here. Now, as we want to verify whether these real eigenvalues are real or not, so let us try. So let if lambda be an eigenvalue of the matrix A, then by the definition of eigenvalue, it will satisfy Ax equals to lambda x for some x non-zero. Now, if you take theta on both sides, so this will satisfy this relation by the property. Okay, and then we have this relation. Now, if you take both side x, here also x, then what will happen? So let us see. So if we take, if we multiply by x on the both side, so this is post multiplication on the right hand side of the quantity. Okay, so then we will get these relations. Okay, now since x is non-zero, so we can cancel this term. Okay, and then we have this one. So lambda equals to lambda bar, which implies lambda is a real number. So we have assumed A as the Hermitian matrix, and we can see that if lambda is an eigenvalue, then it has to be a real number. Although the matrix is a complex matrix, its eigenvalue can be real number. So this, you can call it a parallel theorem corresponding to. Since we have seen the eigenvalues of a Hermitian matrix are real, so you can just now reduce this theorem to the real case. What is a real symmetric matrix? It is a special case of Hermitian matrix. So here also, for a real symmetric matrix, if we have real symmetric matrix, then the eigenvalues is bound to be real. So whenever you have a quadratic form Q, X transpose AX, this matrix is going to be real symmetric for quadratic form. Okay. And this symmetric matrix, if it is real symmetric, then what we'll get? Eigenvalues are real. So this quadratic form, then symmetric matrix, and eigenvalues. They have a close relation. When you will study maximization and minimization problems, then again this concepts will come back again. So this is just for your information. Now these are easy tasks to verify. I would leave it to as an exercise. Verifies these relations. And next thing is to prove any real matrix, any given matrix, it is a Hermitian matrix. So what we have to do? We have to show A theta equals to A. So we'll do this operations, and if we can see, if we can show that this relation holds, then we can call it a Hermitian matrix. These are easy tasks. Though these are named as complex matrices, but their properties are not so complex. They are very much similar to the properties that we have studied earlier. So what is skew Hermitian matrix? Just like we have studied the skew symmetric matrix, here also we can see that skew Hermitian matrix. So this is for skew symmetric matrix. A transpose will be negative A for a real case. Okay. Similarly, if A theta equals to minus A, then we call it a skew Hermitian matrix. So this is a skew Hermitian matrix. A theta equals to minus A. So if we have this relation, then we call it a skew Hermitian matrix. Now for a given matrix, what we'll take? First we'll take the complex conjugate, then we'll take the transpose. So if you can see A transpose, A theta equals to minus A, then we call it a skew Hermitian matrix. Okay. Now we have to study the nature of the matrix, skew Hermitian matrix. So for skew Hermitian matrix, we have this relation satisfied. Aij equals to Aji conjugate and negative -1 will be multiplied. So if you see this relation will satisfy these equations. For I equals to j, aii plus aii equals to minus of aii conjugate. So this relation hold, and this is satisfied because when it is satisfied only if aii, the principal diagonal elements, either they are purely imaginary or they must be zero. Okay. So if you think z equals to purely imaginary identity, okay, then z bar will be minus I. So z plus z bar will be 0. So this relation satisfied. Other case, if you think about z equals to 0, then z bar equals to 0. So 0 plus 0 again 0. So these are the only two possibilities for this equation. Okay. So if we have a matrix I, A1 of this form, then if you multiply with I, then it will become Hermitian matrix. A1, the given matrix A1 is actually now skew Hermitian matrix. Now if you multiply with minus or not minus I, then it will become Hermitian. So yeah. So the next theorem it says eigenvalue of a skew Hermitian matrix is either 0 or purely imaginary. Okay. Now this is a very simple proof because we have studied already the if A is Hermitian, if A is skew Hermitian, then I times A is Hermitian. Okay. Now, with this relation, we will try to follow the theorem or the property, whatever you say it. If A is an eigenvalue of A, sorry, lambda is an eigenvalue of A, then Ax equals to lambda x, this property will be satisfied, this equation. Okay, we have mentioned this is several times. This equation is several times for non-zero x. Now, if we multiply with minus I, sorry, just I, then I times A equals to I times A into x equals to I times lambda into x. So it shows that x is an eigenvector and I times lambda is an eigenvalue of the matrix A. I times A. Okay, I times A. So which is a Hermitian matrix. Now if you use the previous theorem that the Hermitian matrix will have real eigenvalues. So that means I times lambda is a real value. Okay, if it is a real value, then the only possibility is either lambda is 0 or it is purely imaginary. So if you multiply sometimes A times I, you are calling it a real number. This is a real number. The resultant is a real number. what is the possibility? Either A is 0 or A some I. I time x will be -1. So either it is purely imaginary or it is 0. So that is why we say that eigenvalues of a skew Hermitian matrix is either 0 or purely imaginary. Okay. Now, the first property that we have mentioned for any square matrix, any square complex matrix, A is any complex matrix. Okay. Then we can write A as a sum of Hermitian matrix and a sum of skew Hermitian matrix. Just like we can write any real matrix as a sum of a symmetric matrix and sum of a skew symmetric matrix. Okay, so here we can write as A plus A theta and plus I times 1 by 2i A minus A theta. So this is our claim that A can be written as this. Or in simple word, we can write it R plus IS, where R equals to this one and S equals to this matrix. Now the claim is to R is a Hermitian matrix and S is a skew Hermitian matrix. So in order to show that, we have to show that R theta equals to R and S theta, we are supposed to show minus. So this should be minus S. Okay. No, theta is already there, so we'll exchange A minus theta. So both are actually Hermitian now, S and R. So if we multiply I times, for example, S is Hermitian, then IS is skew Hermitian. And we can write A equals to R plus I times S. Okay. So these two relations are satisfied. Okay, we don't have any problem. Okay, now the question is whether this expression is unique or not. The answer will be yes again. For example, if you suppose A can be written as P plus IQ, where both of them are Hermitians, okay, then it is easy to prove that P theta equals to P and Q theta equals to Q. And then if you take this relation A theta, then you will get this relation and you will get two equations for here A and A theta, two variable, two equation. Here you get P and Q as of this form. So which is nothing but the value that we have defined earlier here, R and theta are same. So this is a unique expression. Whatever may be the notation for the matrix, this R is going to be half of A plus A theta, and this S is going to be 1 by 2i A minus A theta. Okay, so this is a unique expression for the expression of a Hermitian of a complex matrix as a sum of Hermitian matrix and the skew of Hermitian matrix. Okay, so this is one particular example for this type of problem. If we have A matrix, then we take a conjugate. After that, we take A theta conjugate transpose. Then we write A plus A theta, which is going to be, okay, then we divide it by half. Sorry, we multiply by half, or we can say divide it by 2. Then the matrix is called as R matrix. Okay. Similarly, we can find S matrix, and this A can be written as a Hermitian matrix and a addition of I times, this is I times the Skew Hermitian matrix. The sum of Hermitian and sum of Skew Hermitian matrix. So these are very simple, easy to verify. So this is what we have so far is the task. Right, try to verify these results, whether they are correct. Now, the parallel concept that we had is orthogonal. For orthogonal matrix, we have seen A transpose equals to A transpose A equals to I. Okay. So, with that notation and the concept, we'll define for a similar concept called unitary matrix for complex variable matrices. For a given complex matrix, if we have this relation, then we call it a unitary matrix. So for a given example, this is a you need to show this is a unitary matrix. So how do we do that? First, we have to write A, then find out A transpose. Then again, we try to find out A theta into A. If this is I, in fact, we have to do one more step to verify A transpose A theta. Verify this is also. Okay. If this is satisfied, then we call it a unitary matrix. Now, properties of unitary matrix, actually mainly we are interested in 4 properties. Property number 1, inverse of a unitary matrix is also unitary. Okay, and the parallel concept is inverse of an orthogonal matrix is also orthogonal. In fact, if you remember the P matrix for a given A is symmetric matrix from orthogonal diagonalization, if you remember, orthogonal diagonalization. You see that P inverse AP was D, and this matrix and this both of the matrix were orthogonal. Go back and check this claim. P and P inverse are orthogonal. Similarly, transpose of a unitary matrix is also unitary. In fact, the transpose of a orthogonal matrix is actually the inverse. So this is again 1 and 2 are actually almost similar type of claim. And the product of unitary two unitary matrix is also unitary. The main important theorem is this one, property 4. The eigenvalue of unitary matrix has absolute value as 1. Okay. So these are just a simple proof. So verify these relations. for a given unitary matrix, since A is unitary, so it will satisfy this equation. Okay, now you have to show that A inverse is also unitary. So you take the inverse on both sides. Okay. And just simplify. So after simplifying, we can see that this is satisfying this. So A inverse is also unitary. Similarly, property 2, it says if A is unitary matrix, then A transpose is also unitary. Okay. So A is unitary means this property will hold. Now you take the complex conjugate transpose. Okay. So if you take this, so you will get this relation, and from here you get this. Now what our aim is to find out this relation. So if you can just transpose, take the transpose from here, then you will get these relations, and finally here. Okay. So this is easy verification. Just go through it, you will understand. Okay. Now the third property, that is, if A and B are two unitary matrices, then AB, the product of two unitary matrices is also unitary. So A is unitary, it will satisfy this equation. B is unitary, it will satisfy these two equation 2. So from these two equations, we can just take the multiplication of AB and AB transpose, conjugate transpose. And this will lead us to write this equation. Because this is I, so we will substitute this. Similarly, we have to prove the other way, other equation also. And we can see that AB is unitary matrix. Just go through it, and you'll be able to verify. Okay. The next theorem, which is property, which is very important. The modulus of each characteristic root of unitary matrix is unity. Now suppose A is unitary matrix. So A theta equals to I. A theta into A equals to I. Now lambda is a characteristic root of A. Then it will satisfy this equation for x non-zero. Okay. Then you take the conjugate transpose on both sides. So if you take this, it will satisfy. It will give you this relation. Okay. Now if you just multiply with Ax on the both sides, then we will get this relation. So from 1 and 2, what happens? So this is 1 and this is 2. So you multiply this 1 and 2. So this is Ax, the left hand side, and x transpose, x theta and A theta. And then it is having this relation. So 2 is multiplied by A, 1. So if you do this, we'll get this relation. Now we just try to simplify. Okay. And after simplifying, we see that since x transpose, x theta and x are non-zero, because x is non-zero, so their product is also non-zero. Okay. So therefore, we must have this relation as 0. So lambda into lambda conjugate equals to 1, which means absolute value whole square equals to 1. So it is nothing but the absolute value is 1. Okay. So this fourth property is also very important. Now, if you try to look into the other problems regarding unitary matrix, then you will see that for a given unitary matrix, the question may be define a unitary matrix. As we have seen that unitary matrix can be defined as a square matrix for which it will satisfy this equation. And then given a matrix, you need to verify whether it is unitary or not, the resultant matrix. So n is given, you take I minus n and simplify it. Then I plus n, you simplify it. Then you have to take the product. First you have to take the inverse, I plus n, inverse, and then you have to multiply with this one, product, and verify whether it is unitary or not. So this is just a simple task because this is a 2 by 2 order, so you can use the formula. So adjoint of I plus n divided by determinant of I plus n. Okay. And then you see that you get the B matrix where B is nothing but a unit, hence the result. So this is a unitary matrix. So B transpose, B conjugate transpose, that is a B theta into B equals to I. So this is a unitary matrix. Okay. Now there is a geometrical interpretation. Okay. Because we have seen that Hermitian matrix, they have real eigenvalues. So if you consider about the complex plane, all these are real eigenvalues. So eigenvalues of the Hermitian matrix will lie on this line. Okay. On the real line, because they are real. For symmetric matrix also it will satisfy. But if you think about the eigenvalues of the skew Hermitian matrix or skew symmetric matrix, they will lie on the y-axis, that is imaginary axis. But if you think about the orthogonal or the unitary, then you will have the eigenvalues will be here. Within this, they are in. So these are the unitary matrices. They will lie on this. Their this length will be 1. Radius equals to 1. The unitary, for unitary matrix, the absolute value of the eigenvalue, that means is equals to 1. So for lambda equals to 1, absolute value of the unitary matrices, the eigenvalue of the unitary matrices are equals to 1. So they will lie on this line, on the perimeter of the circle. But if you think about the eigenvalues of the skew symmetric matrix or skew Hermitian matrix, they are on this vertical line, imaginary axis. And these are real axis for Hermitian matrix. Now there are some tasks to verify for skew Hermitian matrices, for unitary matrices. So try to verify these 5 problems. Okay. So if you have any doubt, you can ask me. I will stop here today.